Hello, in the previous video we talked about the training process of neural networks. In this video we want to see how can we accelerate this process and make it much faster. Okay, let's start. Okay, so far we saw that for each epoch we are going to have x as the input to our network, which is 100 by 1, and then we are going to calculate the y hat, and the y hat is also 100 by 1, and then the difference between y hat and our target y is going to give us the loss. If we do that for every iteration that we are updating w, we are going to consider all of the x's. So it means that for our database that we created, for all of these data points that we have, we are going to observe all of these data points and update w based on them. And you can see that's gonna be very time consuming and very redundant, because basically we don't need all of these points for finding the w and b. So even with very few number of them, we should be able to draw the line. Because of this redundancy in data, so we prefer to not to consider all of the data. The other reason is that as if we don't do that and the data increases, for example here we just had 100, let's say we might have 1000 data points. So now I have a 1000 data points, and you can see if I just plot that, it's gonna be a lot of these data are actually redundant. And if I want to update w for each iteration, I have to consider all of these data. So in reality we don't do that. We just consider one sample at a time. So we call that a stochastic gradient descent. So let's do that. Here, instead of calculating loss function based on y hat and y, we are going to calculate that for each single data point. So for doing that, let me do this. I'm gonna create a new one. Let me actually keep this because at the end we might need that to plot the loss function. But for here, I'm gonna do this. I'm gonna say for x and y, and I'm using intentionally small letters because we want to emphasize that that is just the one sample. It's not the whole x. In zip of x and y vectors, for them I'm going to predict one single sample and say small y hat equals w times x plus b. Okay, so it's just gonna be one single sample. Now let's calculate loss. We say loss equals torch dot mean of small y hat minus y to the power of 2. Okay, now we have to take the derivative of this loss. So we just use loss backward. Now again, I need to update w and b. So I'm gonna put them inside this for loop. Again, zeroing the w and b gradients at the end of each calculation, and that's here. And at the end, we should be able to plot the final results after each epoch. So this time, for each epoch means that we are going to observe all of the data. But for inside the epoch, I'm gonna go and see each individual x. Okay? Okay, let me also change this name because this is our batch loss. This is for entire of the data for each epoch. And I just put this here. This is actually the loss function that we are going to take the derivatives and update the weights based on that. Again, this one here is just for plotting. Doesn't do anything else. And okay, so we have that. Let me initialize weights and run it for 100 epochs. Okay. The first one, after the first epoch, consider that here our epoch means that we are going to update it 1000 times because we had 1000 samples this time. And after updating for 1000 samples in the first epoch, we got the w and b. And then for the second epoch, again, for the next 1000 iterations, we got W2 and B equals 2. And you see in a very few number of epochs, we are able to update the network. At the end, we can plot the loss function, and this is the loss that we just recorded after each epoch. We run that, and we see after very few number of iterations, we get that to the optimum. If you remember from the previous lecture, so we had, for example, let me again run this for 1000 samples. So for 1000 samples, we had this data, and there we initialize the network, but this was our loss function that we take the derivative here is considering all of the x samples. So now x is 1000 by 1. So this loss function is based on the 1001 and is going to update the w based on all of them. So if we run that for 100 epochs, so this is a batch gradient descent. So you see it takes much more time. This was the initial. This is after one epoch, means that after seeing all of the data set. But for iteration, it's just updated once, because W and B for batch gradient descent is gonna be updated only once, unlike the stochastic that it got updated 1000 times for one batch. Okay, so if we plot the loss function, so you see, for getting to the optimal value, I need to run it for 100 epochs. For stochastic, I just need to run it for few epochs, and we can save a lot of computation here. That's the reason we mainly use a stochastic gradient descent. So in our training, instead of going over all of the data, we are going to go over samples and update the weights based on them. Okay, the term stochastic here just means that we are going to go over the samples one by one. And because of this fast updates of the weight and bias, now it doesn't matter for us how big is our database. So maybe instead of 1000, we have 10,000. We can easily scale to a larger and larger data sets, because now for each epoch, we don't need to update weights for all of the database at the same time, and we are somehow using the redundancy of the data, and we update the weights based on every single sample. And because we can get to the optimum values very, very quickly, we actually don't need to go for a very large number of epochs like what we did in a batch gradient descent. For example, I can say I just need to run it for maybe 10 epochs. Let's initialize again and run it for 10 epochs, and we should get the optimal value and loss function. Okay, that's the main benefit of a stochastic gradient descent. With a very few number of epochs, we can get to the optimum value of the weight and bias. Okay, this is all for this session, and thank you so much again for watching this video.